This video is about expressing complex mathematical ideas using quantifiers. Let me use the same example as in the previous video. There exists an x, which is for all y, x is less than or equal to y. So this is saying, here my domain is natural numbers. This is saying that there exists an x which is smaller than every other y. Oh, sorry, which is smaller than every y. There exists, I don't want to use it. There exists x which is smaller, which is less than or equal to every natural number. But suppose I want to express a slightly different statement. Instead of for every natural number, I want to say there is an x such that it is less than or equal to y for every natural number other than itself. So how do you express other than itself? The way you do this is, I'll just say, write it down. There exists x, is there for all y. X not equal to y implies x less than or equal to y. That's it. So what the first phrase is doing is it's forcing y to be different from x. And y implies, remember the implies is a nice thing, the nice property that whenever the first part is false, the whole thing becomes true. So here the first part will be false when x is equal to y. So it's saying that when x is equal to y, the whole thing becomes true. And so you don't even care about that case. So let's leave that case out. Okay, so that's why I'm using implication and not and or something. We use implication because we do not care about the case x equals y. Right, so that's it. And to express the mathematical property of being other than itself, you use not equal to y followed by implies. So we use there exists to say that there exists at least one solution. Now, what if I want to say that there is exactly one solution? So this is the property I want to express using logic. And the way we do this is, first we say that there is at least one solution, and then any solution equals this solution, and that will force uniqueness. So let's start with a simple example. There exists x such that x squared is equal to 0. And here I'll keep my domain natural numbers. Actually, I'll expand my domain to now be integers. So is it true that there exists an x such that x squared equals 1? Yes, 0. That works. This has truth value true. But it is further true that there is a unique x, that only 0 is the solution. So how do I express this using logic? So the way I'll say this is there exists x such that x squared is 0, and if there was a solution y, I'll use z, for any solution of z squared equal to 0, we must have x is equal to z. Let me remove some brackets to simplify our life. All right, let's parse this slowly. First part is saying that there is a solution. Second part is saying satisfying x squared equal to 0. Okay, so there is a solution of x squared equal to 0. But further, now I'm saying and for every solution z of z squared equals to 0, we have x equals to z. And so the solution is unique. There exists xpx is at least one solution. Now, if you want to convert this into there exists exactly one solution, you start with the same thing. You have to have there exists. Then you change px to the following. Px and for all z, pz implies x equals z. So the second part is expressing the uniqueness. That's it. It is complicated. Nested quantifiers are complicated, and it takes a while. Like, I'm making this video, but this is the second take of my video. The first time I messed up. That's just how it is. Even after you have been doing math for a long time, it takes a massive effort to get this right. But then now if you look at this expression, it is like unambiguous. If you can read logic, you can understand what this is saying without any doubt. And that's the whole point. Even if it takes more work, that's totally worth it if in the end there is no ambiguity. Okay, so that is how you express at least one solution. So the slightly more harder example I want to do is the same one I started with. Now my domain is natural numbers. I want to express the fact that there is exactly one smallest element. Okay, so there exists x such that for all y, x is less than or equal to y is expressing that there is at least one smallest element. Now I want to change this to there is exactly one smallest element. And how we'll do this is I'll do it carefully in steps. So for all there exists x, for all y, x less than or equal to y is my original proposition, predicate. Now I'll take whatever is after there exists x, and this is the part I'll change. So this is my p. This is going to get replaced. So I won't even look at there exists x for now. I'll change this to for all y, x less than or equal to y. That won't change. And now I need to throw in a new variable z, such that for all z, z replaces x, for all y, z less than or equal to y implies z is equal to x, and this goes inside one bracket and this goes inside another bracket, and there exists x just comes along for the right. Whew. So this thing is expressing uniqueness.